Hello to everyone. Today I will be talking about the early decomposition and the ambiguity resolution problems. This is the second presentation within the context of Philosophy of Computer Science series. The table of contents, you can see it here. First, we will have the definition of the terms, and then first I will explain the early decomposition problem, then the ambiguity resolution problem, and then we will have a discussion over the competences to address these problems, and I will refer to the research work. Well, inherent problems do not have easy solutions. So the problems that I will be discussing now, they are so-called inherent problems. But very important thing is knowing what we cannot be knowing at all help us in widening our worldview and in understanding the fundamentals of science and engineering. Therefore, I consider by myself very important to know these inherent problems. Well, this is a part of what I would call philosophy of computer science talks. And this is my second talk. The first one was about the imperfect information problem. And in this talk, I will basically present two additional problems. And the early decomposition and the ambiguity resolution problems, these are actually a special case of imperfect information, the imperfect information problem. So the remaining talks in the future will introduce the constructibility problem, the hermeneutics problem, and so on. Well, you can find the video of the first talk. I have given here the video address, the link, and you can follow it. I think it's important to understand also this talk. So I advise you to refer to follow that video as well. So, of course, we are referring to all kinds of terminologies: philosophy, philosophy of science, philosophy of computer science, software engineering. These are, I'm referring to standard definitions. I took them from Wikipedia. What is important, however, especially for this talk, is to understand what is perfect information and what is imperfect information. Perfect information is information that contains all the attributes and values with sufficient precision and certainty for the purpose for which it is used. Imperfect information is information, obviously, that's not perfect. So, in fact, this is philosophy, this is software engineering, this is imperfect information. So we are actually discussing the overlapping area by these three symbolic circles. Well, also as I presented in the first lecture, first presentation, inherent problems are the problems that cannot be solved perfectly. Nevertheless, acceptable solutions may be found in practice. A very important aspect of these problems are in the problem space, which means that no matter what technology you use, no matter how the technology is advanced, still you may not address and solve these problems. You cannot, in fact. Competences for solving inherent problems. We will also look at the competences that you need to solve these problems cannot exist in our physical world. Of course, I'm talking within the context of computer science and software engineering, but you can easily generalize these problems to the other disciplines as well. Well, let's see now what the early decomposition problem is. We know that today's systems are large and complex. We therefore have to divide complex problem into sub-problems and try to solve each sub-problem. And then in the end, of course, we hope to solve the overall problem. When we design a software system, also we have to divide it into subsystems, sub-problems. For example, for the purpose of analysis, for the purpose of design, for the purpose of realization, for the purpose of maintenance. The early decomposition problem in design states that if the partitioning of a software design problem is carried out too early in the design process, it may be possible to reduce the complexity of the design because you are dividing it into pieces, but assuring the optimality of the resulting design can be too difficult to fulfill. Because it's too early, that means you have not yet understood the problem very well, but it's too complex. You need to divide it into pieces. You hope, of course, that because of subdivision, you simplify the problem to a certain degree, but the subsystems are not ideal because of too early decomposition. Early decomposition problem can be classified as a subset of the imperfect information problem. This is because the early decomposition problem can be experienced when there is no sufficient knowledge about the systems that are designed. So as we show here, this circle represents philosophy, software engineering, overlapping area, and then here we have the imperfect information problem area, and early decomposition is a subset of the imperfect information problem. Partitioning of problems into sub-problems and try to solve them, each sub-problem individually, and then integrate the solved problems into one overall solution is not new. For example, you can refer to the dynamic programming approach. In dynamic programming, a complex problem is simplified by breaking it down into simpler sub-problems in a recursive way. Of course, the nature of a problem must be suitable in decomposing it in this way. In other words, the solution to a given optimization problem must be calculated by the combination of optimal solutions to its sub-problems. But in order to apply the dynamic programming algorithm, you must have enough insight in the nature of the problem to categorize the problem as a dynamic programming problem. In our context, however, we refer to the general problems which are not well understood due to imperfection, and then therefore we don't know exactly what the problem is. Of course, it's a very complex problem. It includes many sub-problems, and therefore we cannot apply such a technique because we don't know the problem yet. So, in fact, the early decomposition problem is a paradoxical problem. So, there is also so-called multi-stage programming, where in multi-stage programming, compilation of a program is partitioned into series of phases, allowing type-safe runtime code generation. The programmer qualifies expressions by notation that specifies the phase at which they are to be compiled. This enables specialization of a program at runtime, and as such, performance of programs can be enhanced. But this is quite different from what we want to do, because an important difference between the early partitioning problem and the stage optimization problem is that in the first problem, the software engineers most likely are unaware of the details of the system to be designed, since they are still in the early phase of software development. Therefore, they might not identify the optimal boundaries of partitioning. Whereas in the latter, we can assume that initially the optimization problem is known, but the optimal solution is yet to be searched. So multi-stage programming is quite different from the early partitioning problem. Now I will present the ambiguity resolution problem. The ambiguity resolution problem, which is represented by AR here, is a subset of the early decomposition problem. The early decomposition problem is also a subset of the imperfect information problem. We will elaborate on the ambiguity resolution problem from two perspectives: the early resolution problem and the lack of expressivity problem. Early resolution problem states that if there are alternative resolution considerations, and if the alternative resolution considerations are eliminated too early by committing to one of the alternatives, in this case, loss of information may occur. In case of imperfect information, there is a more chance that this problem can be experienced. The early resolution problem in design, this problem appears if there is a complex design problem influenced by imperfect information sources, and the design notations are assigned too early to the elements of the problem, then loss of information may occur. For example, if you are doing object-oriented design, you are not sure about whether it should be an object or it should be an attribute or association, whatever, and you make a choice and you say, okay, this thing is a class, for example, in object-oriented notation, and you are not sure about it, and the uncertainty actually is there, but you make your choice, and inevitably, of course, you lose information, especially if it is committed too early without knowing the details of the problem. Well, the second case in this problem is the lack of expressivity problem. This problem appears when there is no language expression that can represent intended meaning in an effective way. So you observe a problem and you want to express it using a notation, but you cannot express it as you want, as precise as you want, and then you are forced to choose to one of the available notations, then the same problem appears because you lose information, because you cannot express exactly what you want to express. These two cases are not mutually exclusive. In case of the early resolution problem, if alternatives are not eliminated, the complexity of the design process increases further. Nevertheless, if you can manage the complexity, and by not committing too early to one of the alternatives, then acceptable solutions can be achieved. However, in case of the lack of expressivity problem, no adequate solutions may be found, even if the complexity is managed, because you cannot express what you want to express. Now we will discuss the competences to address these problems. The competences to address the problems of imperfect information are also valid for the problems of early decomposition and ambiguity resolution. These were the problems we discussed in our previous talk, and these competences are still valid here. So I advise you to look at the previous talk. Here is the address of the video which you can find. In addition to that, we will discuss now additional competences. Well, what is a competence? Competence is generally defined as the mutual existence of the necessary knowledge, skills, and attitude. to address the problem that is considered. I want to now refer to the all-knowing competence within the context of the early partitioning problem. What is the all-knowing competence? There is sufficient knowledge about the systems to be designed so that it can be partitioned optimally. Now I will define the all-expressing competence, which is defined as follows. The competence is to master all notations, languages that make it possible to effectively express all intended definitions of the design. If you have this competence, you will never have the problem of lack of expression. In this slide, we see two universes. One is the universe of inherent problems, and the other one is an imaginary universe of non-physical competences. There is an imaginary boundary, and there's a wall there, there's an imaginary boundary. We can never cross this gate. We can never enter into the imaginary universe, which is depicted here. However, progress in science will bring us closer to this wall. The problems we are discussing, the imperfect information problem, the early partitioning problem, the ambiguity resolution problem, these are all in the universe of inherent problems. On the other side of the wall, there are competences that are, these competences are necessary to address these problems. The first four all isolation, all infinite, all always, all at once, we have discussed these in the previous talk. In this talk, we have introduced two additional competences, all knowing and all expressing. Now we would like to refer to the research work. In particular, we will refer to our own research work. Well, in the previous talk, we also listed our publications, our research work, and you can refer to that presentation as well. Well, how to deal with these problems? First of all, we would like to, of course, improve competences in the domains of the design problem. So I would advise to adopt domain-driven, or we also call it synthesis-based design methods. Secondly, adopt domain engineering techniques, use domain-specific models and ontologies that are related to the identified problems in the presentation and related to the problem solution domains of the design problem that is considered. Domain-driven design, synthesis-based design, and adopting these domain models can help you to understand the problem better. Build a domain-specific asset base where you gather all kind of domain information. Adopt model-driven engineering techniques. These are, of course, all related techniques. Adopt expressive, multi-paradigm, extensible, compositional design notations and languages. Obviously, having expressive design notations can help you to overcome these problems. Well, I'm referring to one of the publications which we had, and here we defined the early decomposition problem. In this paper, this was in 1992, we have already presented the early decomposition problem. You may also adopt feedback control systems, feedback control architectures to minimize the errors due to the problems discussed in this talk. You may claim that ambiguity resolution problem can be addressed at runtime, for example, by designing an adaptive control approach, which is symbolically shown here, which selects the best alternative for a given context. Such an approach may help indeed in dealing with this problem to a certain degree. However, it does not let the problem disappear completely, since designing a control system has its own alternatives, and committing to a certain control system also results in loss of information in its own context. I would advise you to refer to this paper where we actually refer to dynamic, adaptive, and reconfigurable systems overview. And here in this paper, we give a prospective vision. You may also use product line engineering techniques. So let us remember what the product line engineering approach is. In product line engineering, a design process is divided into two parts, domain engineering and application engineering. In the domain engineering phase, the alternatives of a product family are specified. Most of the time you use, for example, feature models. In the application engineering phase, the alternatives are configured to obtain concrete software products. There are, however, some challenges in using feature models within the context of product line engineering. You have to decide the granularity of features. And in general, features correspond to software building blocks. If feature models are very fine-grained, the number of possible product configurations can be too large. As a consequence, the software engineer may have difficulties to select the best configurations among many alternatives. On the other hand, if the product configurations are large-grained, it may not be possible to configure the product with the desired features because you don't have the right granularity, possibly. There are also other problems. Feature models evolve too. Assume that you have configured certain products and you delivered them, and feature models evolve at the same time. Coping with the evolution of feature models and their impact on the configured products can be a challenging problem to deal with. Finally, configuration of products from existing features may not be always sufficient to create the desired products. In general, additional cost must be written as well. Here you see some publications related to our domain-driven design. Here you see the list of publications, and there are some pictures represent or refer to these publications. I advise you to read these papers in order to gain a feeling of what domain-driven design is, or what the synthesis-based design is. We have worked also on ambiguity resolution, and in particular, leaving inconsistencies in the design models. Alternatives in design are expressed in suitable design notation and are kept during the refinement process of design. When there is sufficient confidence, ambiguities in design are removed. There is one paper here I'm showing here, and this paper gives a good overview of the ambiguity resolution problem. In our work, which I am listing here, in our work, we adopt fuzzy rules. Design rations are formulated in fuzzy rules. Contextual information is formulated by adapting the definition of the corresponding fuzzy sets. Fuzzy design models are preserved as long as possible. New information sources, if become available during refinement, are fed into the fuzzy reasoning system, and as such, the corresponding fuzzy design models are adapted accordingly. When computable programs are to be obtained, fuzzy design models are defuzzified and transformed into traditional design notations. These publications have shown that differing resolution of ambiguities improves quality of design. On the other hand, of course, complexity of design increases accordingly. Here are some publications actually referring to differing decisions for ambiguity resolutions. And we have proved in a number of papers that actually the quality of design improves if you can differ. Here in this slide, I am showing you some of the publications we have made related to the imperfect information problem. I have presented these publications and also the other related work related to the imperfect information problem. Therefore, I am not going to repeat them here again. You can refer to the previous talk. And here is also explanation of the references and the terminology and our contributions. And here is a list of papers, especially the first one and the ones fifth and the remaining papers are our papers related to the problem of imperfect information. And you can find more information in the previous talk. Thank you very much for your time. Have a nice day.